So I'm very happy to present you here Antonio Cauchi from Concordia University. He is going to speak about algebraic cycles and Funtorial leaps from G2 to PGSp6. Okay.
So thank you again for the invitation. And oh, now I can see myself. Wow. Okay, that's gonna be weird. Okay, so it's okay. Okay, so like I'll try to write as big as I can so that everyone can see it well. If somebody online cannot see it properly, please tell me. So as this kind of like what do I want to say? So the series of seminars is quite automorphic, right? So the idea, like the motivation I will give in these talks is related to a function. And in particular, when we want to define an automorphic function, this is the kind of a function we want to look at, it will depend on a complex parameter S. There will be caspital, if caspital makes sense, but caspital automorphic representation of a group G. So today, like we want to suppose that the group G is over Q. So we will have, just for simplicity, so like a group G is a reductive group over Q, and we take a representation of the adels, of the Tate groups, of the Tate points of G. And the extra data that we want to do, that we had to take following Langlands, is a certain finite dimensional representation of the Langlands dual to the group G. So this is a function, and I'll place, like, I'll put an extra data for now, which is S, capital S. Actually, I'll just call it sigma, where sigma is a finite set of primes which contains the bet primes for pi. Then this L function can be defined as an Euler product for all the primes P not in sigma of L, S, pi P, RP, where what pi P is the P component of our automorphic representation, and RP is the same representation of R, but now we are seeing it as a representation of the Langlands dual group of G as a group over QP. And indeed, we can go a little bit further, like I'll tell you how these guys are defined. So this is clear, yes. Okay. So at the end of the day, this is nothing but the determinant of the identity minus RP A pi P, P to the minus S. Where I haven't told you what A pi P is, this is the Frobenius conjugacy class associated to pi P. In other words, this is the matrix that can be taken diagonal inside the dual group of G that contains the Tate parameters. Of pi P. Okay, so somehow the theorem or proposition that one the first proof is whether this converges somewhere. And indeed, the idea is that for data pi and r, and of course, I mean, I'll add sigma too, sigma pi and r, this is a function L sigma S pi R converges absolutely. In a certain region, let's say where converges absolutely in the region of the complex plane where the real part of S is big enough. And one can be precise about this, and I'm gonna present it in 1 second. And actually, the conjecture of Langlands says the following: so that there should be a good definition of Euler factors at P. Let's see if I don't forget anything. So for every P in sigma, there should be a certain Euler factor L S pi P R P, and a local root number, so that I'll denote by epsilon. Again, that depends on pi p. It actually depends also on a character of the adels, but we don't care now about this. Such that the following is true. And for this, I'll start taking up here. And maybe I'll write a little bit smaller. So the result is the following. The conjecture is the following, such that there should be local Euler factor at ramified primes together with certain root number associated to P again, such that if we now consider the function completed at all these primes, so this is going to be the product for P in sigma of these Ls by P R P times the partial function that I defined before. Then this extends to a meromorphic function over the all complex plane, and I mean it extends to a meromorphic function over C with finitely many with a finite number of poles, and such that there is a relation between around the central values that relates Ls pi r and up to a certain like sign that I'll define in a second. Pi r relates so the value at S of the L function to the value at 1 minus S of pi r. I mean, technically we should put the dual here, but so there should be this functional equation such that Es pi r is going to be the product of a sign at infinity that I'm not maybe telling you much about it. Actually, not right now. So it's going to be the product for P in sigma of E S pi P RP. So implicitly, what we are assuming is that this like root number is just one at every ramified place for pi.
There, the automorphic representation on the right-hand side needs to be by dual, no?
The contragradient.
So you need to.
Here.
It's not self-dual.
Okay, most of the time we're going to work with self-dual stuff. So this conjecture has been proved not in the old generality, but somehow like looking at these functions case by case. But what I want to say, and this is a remark, that if the representation pi is tempered, meaning that each local component is tempered, then just on the nose, one can show that LS pi R converges absolutely for the region of the complex plane such that the real parties of S is bigger than 1. So now, if we work with something that is tempered, and suppose that we have like a condition of this kind, there is somehow an interesting region where we want to understand the values of this function. And the interesting region is where the real part of S is between 1/2, which is our central value, which will give our central value, and 1. And I think the talk of last week of Andy really focuses on the value, on the like the arithmetic meaning of the value at 1/2 of a certain L function associated to GLN. So, or product of things from GLN. So what we're gonna do now is to look at what happens at the value S equal to 1. So in particular, so as we said, this L function will converge absolutely for this region. So it's automatic and holomorphic L function in that it's an holomorphic function in the region. So the question somehow that the one can ask is, when does, suppose that you can now extend the L function to a meromorphic function, what does, when does L sigma S of pi R obtain a pole at S equal to 1? So there are various like works on this direction, and this is not exactly the question that I'm interested in today, but I'm gonna get to it. Yes, of course.
This G, the group is any group.
For now, it's
the group is any group.
It's any reductive group.
But this stuff that you just erased, that's for temperate,
yeah,
is true for any reductive group.
So the point is that the point is that the definition that you can take of a local component of pi being tempered is that the absolute value of the eigenvalues of its Tate parameters have the absolute value is equal to 1. So then what you have like what you get is the Euler product of things like determinant of 1 minus certain alpha i's, like a matrix of alpha i's p to the minus s to the minus 1, where this now alpha I have absolute value 1, and this converges absolutely as long as S is as real part bigger than 1. This is just so it's valid for any group. It's just like a result of complex analysis, rather.
May I ask you a question?
Yes, of course.
So are you including the Archimedean places in your sigma? So is this pose related to some pole of a gamma function or not really?
Yes, I am. I put this under the rug, but I am. Absolutely. And okay. Indeed, in the, like I should have said it maybe, because when I wrote the functional equation, you should complete the L function with another product at infinity. That's actually a good point. So the exactly will detect you when you have critical values or not. So so coming back to this L function, when does obtain a pole that is equal to 1? Somehow what you could expect and I'll put myself in the case where only a simple pole can happen and not pole with further multiplicity. One could expect to relate the following three things. So that L sigma S pi R as a pole, as a simple pole at S equal to 1. 2 is that a certain automorphic period is non-zero. And with this, I mean, there's something like this. There's going to be a certain subgroup H of G, such that maybe mod up by the center, and I'm going to make a remark on this. DH is non-zero for some phi and pi.
Sorry, Antonio, can I ask you something?
Yeah.
In the first point, you say that you expect a simple pole at S equal 1, but
I expect, sorry, to relate. To relate three things.
okay. So yeah, because if you take a Caspidal form for GLN, so you have it's holomorphic. So
exactly. So you expect to relate the existence of a pole at S equal to 1 to the fact that a certain period is non-zero. And here I'm assuming, and for all the talk, I'll assume that pi as central character, as trivial central character. And the third thing that one could hope to relate to the existence of a pole is that pi is maybe a weak functorial lift with respect to the inclusion of a certain group H prime inside the Langlands dual of G, such that, yes, I'm going to change the pen because it's dying. Is that now we're going to switch to blue, I guess. So such that H prime, oh wow, is a stabilizer of a generic vector big enough vector for the representation rho or R. How do I call it? For R. And somehow now the question that we were interested at and somehow motivates our work is, okay, suppose now that the L function is motivic. And that the relation 1 to 2 to 3 holds in a certain way. So the question is, which arithmetic implication does this relation have? So the question is now, okay, suppose that we have a pole, suppose that this is equivalent to a certain period being non-zero. Does this say anything about the motive associated to pi? And the answer is, well, it depends on the context, and there are lots of arithmetic applications to relations like this. So before describing what's the real matter of my talk, I'll give you an example. And the example is, at least for someone in the audience, very familiar. And to get more disciplined, let's see if you agree on this, more discipline on my writing, I'll like divide the board into. You should have told me before. It's like.
Modification is there.
Because otherwise, you know, I always keep writing. Okay, so section 2 is going to be an example. It's always, especially in this theory, it's always good to keep like a lot of example in mind. Otherwise, most of what I say might not make sense. So take pi to be a cuspidal automorphic representation of PGL2 AF, where F is a real quadratic extension of Q. Okay, you have to imagine that this is generated by, could be generated by a holomorphic Hilbert modular form of with trivial central character. And to define the L function, we need to choose a representation of the dual group, and we're going to choose the aside representation. So just for people that are not familiar with this, so I'm going to, PGL2 is my PGL2, actually, like I'm going to write it here. So remember that our G is going to be the restriction of scalars from F to Q of PGL2, PGL2F. And so what is the dual group of Langlands dual of G? This is going to be GL2C times GL2C. Sorry. It's not GL2. Because we're working with the projective group, so it's going to be SL2C times SL2C. And then we have to take care actually of the fact that now our group gets split over F. So there is this extra factor given by the Gala group of F over T. So the aside representation is a representation that is 4-dimensional. So that lands in GL4C. Again, it actually lands in SL4C, but it doesn't matter. There is a natural candidate for this group, no? SL2C times SL2C. We take the standard representation of one guy, standard representation of the other guy, and we take the tensor product. However, we have to take care of this Gala, of the action of the non-trivial element of this Gala group. And so one defines RG1, G2, and sigma in the following way. So it's going to be G1, G2, meaning that we take the tensor product of the two representation, we make them at component-wise, and we see it in a 2x2 block in GL4 if sigma is trivial, and
You mean diagonally, no?
diagonal block, yes. I could actually do it. G1, G2. And
But this is not the tensor product.
it's true.
This is the direct sum. You said tensor product.
It's true. I wanted to say direct sum. It's true. good point. Yeah. And this is if sigma is not 1. So like my only point is that you want to extend this representation non-trivially because you have to take care of this guy. So the point is the following. Let's look at PGL2. It's like
excuse me, Antonio. May I say something? I think what you want to say is so you have like C2 times C2, which is your vector space for each one of them, and then when you take the tensor product, it's like C4.
Yes.
And then what you're saying is that you want just G1 and G2 to act on each one of the parts of the tensor product. And in the second case, you want to act in the opposite way, but it's not this four-dimensional representation. This is the direct sum, right? So it's not going to give you exactly what you want. So I think what you were trying to write is correct. You want G1 G2 to act on the tensor product.
You're right. So like I'm gonna because the vector space. So you take the standard representation of the first, you take the tensor product of the standard representation of the second, and then you have the G1 and G2. So this is now a four-dimensional.
I was wrong, so it was.
Yeah, thank you for like, this is important that we don't mess this up, especially for what I'm gonna say right now, which was, you see, like I would have discovered the mistake in 1 second, because I would have told you, take PGL2 over Q.
Okay.
Now the dual group of PGL2, and I'll call this H, and the dual group of H is SL2. SL2 embeds diagonally in LG. And so you can look at, I'll call this iota. And so you can look at the pullback of this representation, or so the pullback iota star of R, but what I actually mean, you look at R and you consider it as a representation of LH. So as a representation of LH now, notice that LH will embed with component of Galois group that is just equal to 1. So in particular, we're looking at the standard tensor, the standard restricted to SL2. So this becomes equal to the standard tensor, the standard to restricted to SL2. Diagonally. And this is a four-dimensional representation, which is not irreducible anymore. And how does it factors through as the symmetric square of the standard plus one trivial line that I'm just called C. And here is the consequence. Now, suppose that we look at a representation. So take pi such that A pi p, so the Satake parameter, and actually A pi, let's call it V, that is better. The Satake parameter A pi V belongs to the image of the dual group of H. Then if we look at the determinant of identity minus the norm of V to the minus S times the image of R of A pi V. Now this product, since there is this decomposition, now it's a block decomposition. This determinant will split as follows. So there's going to be the determinant of I minus NV to the minus S of the symmetric square, sim square of A pi V times what? Times the determinant of 1 minus N minus Vs. So this is 1 minus NV minus S times 1. And what does it mean? So this relation means that if you take now pi such that this is true for all V, you somehow expect the global F function, partial global F function, as a pole at S equal to 1, because now you have that the SI is going to be somehow the product of a partial F function associated to the symmetric square times like a partial Dedekind zeta function associated to F. And this guy has a simple pole at S equal to 1. So if you put yourself in the situation such that this does not have a pole at S equal to 1, it seems that there is a strong relation between being a lift from this HL and the poles of the SIL function. And indeed, that's the relation that I'm going to write here. So L sigma of S pi, I'll just write aside, as a simple pole S equal to 1. This is equivalent to the integral for a certain phi h dh over GO2 moved out by its center is non-zero for some phi in pi, and it's equivalent to pi being the base change from a representation of GO2 over G. And the point is that the geometric applications of these pictures have appeared in many works, starting with the study of Hirzebruch-Zeige cycle. And so, Kudla problem, and so on and so forth. And why is that the case? Because these periods have an automorphic, have a geometric interpretation. Like these are nothing that the integral of certain differential forms associated to the cast form phi over the, they can be related to the integrals of a certain automorphic, differential form associated to the automorphic cast form phi over the modular curve. And so what we are going to do today is going to be look at a similar relation where now the groups become a bit more complicated, and deduce certain interesting arithmetic applications.
Sorry, can I ask you a question?
Of course. Please.
The first one, what is special about F being real quadratic? Can it be totally imaginary quadratic?
There's nothing special. It was just to fix the ideas on something simple.
Okay, maybe the applications are not.
You could start from F and you take a totally real quadratic extension of F. So you could take E over F such that they are both totally real and is a quadratic extension, and all of this would make sense.
I'm more interested in you take the base field Q, for example, and F, the imaginary quadratic, mean the Bianchi case, because Luis like a lot.
Exactly.
So
In that case, this relation is still interesting. In the geometry, you don't have Shimura varieties in that case, so things get a bit more.
I have the impression that was used by Paquin Lee.
Yes,
exactly
Paquin,
here to construct the
exactly.
p-ádica function. No?
Exactly. Okay, so let me come. I'll comment this that it's.
It is true, Paquin, or not? I'm saying.
Yes, it's true.
Yeah, but as Antonio said, there's no geometric analog of these algebraic cycles.
But nevertheless, you can look at a Betti construction using this period and still interpolate a p-ádic value for the base change.
Oh, great.
Yeah.
By the way, I take the disadvantage to say the publicity that in few weeks, maybe, Paquin is going to give a talk exactly about that.
Oh, that's nice. So tell me when it is so I can.
Well, I don't think the date is known yet.
Yeah, but soon you will know.
Okay, yeah. Please tell me, Daniel.
It was just like this was just to fix some ideas.
May I ask you a stupid question, Antonio? So
no question is stupid.
What are you integrating over GL2? Is it PGL2 or it's really GL2?
It's really GL2. So I'm really integrating here. No, that's not a stupid idea at all. That's a stupid question at all. So I'm integrating over GL2, a Q over GL2Q, but I have to quotient like out by the center.
Okay.
And this is because I'm assuming pi to have trivial central character.
Yeah. Okay.
It goes automatically there.
Yeah. Okay.
No, but this is good that I fixed it and somehow somehow like if I had more time, if I would have given like a 3-hour talk, I could have looked at the case of Shalaika periods, and I know no. There was a joke. I'll try to finish in 1 hour and a half max. I know that we have 1 hour, and that's not. It was just a joke. Okay, so I'm gonna start introducing one of the main characters of my talk and my work with Francesco and Joaquin, which is given by an exceptional group. Before starting this project, I really didn't know what this exceptional group was, so at least I learned something non-trivial. So if you take H to be the algebra of quaternions over Q, one can consider the direct sum that we'll call O, H plus H, where like the elements will be denoted by A plus LB, where L is an imaginary unit such that L squared is equal to, belongs to plus or minus 1. One can make sense of a product over O, which is not going to be associative. By the way, for us today, we'll take L to be equal to 1. L squared to be equal to 1. This gives rise to the split octonions. One could, if instead one takes the imaginary unit such that L squared is equal to -1, gets the compact octonions. And so to this octonion, one can define a product. It's going to be non-commutative. It's going to be non-associative. So it's very, very complicated thing, but one can give a quadratic form, one can define a quadratic form of it using the norm, and given by complex
so this
conjugation.
L doesn't
Yes.
belong to H.
Exactly.
So you
It's
should
like it's an imaginary in the sense that you want to make sense of we want to give a basis
I see.
of the octonions. Yeah.
But maybe in the right hand side is better to write H plus LH. No?
Yeah, exactly. Or maybe it could be better to write it as AB, right?
Okay, it's just a notation.
But yeah, it's like. So the point is that one can consider the traced zero octonions. Which I'll denote by B7. So basically they, if you look at this basis given by 1 I, J, K, and then L, the first coefficient is going to be 0. And the funny fact is the following. So if you define G2, the group over Q given by...
Sorry that I bore you with this basic question. So but what is B7? I am confused.
Yes, it's going to be the 7-dimensional, it's a 7-dimensional Q vector space inside O given by the traced zero octonions. So there is a trace from the octonions to Q, which is basically take X octonion, take its take the sum with its complex conjugate, and you take the sum. This is the trace, and you ask that the trace is 0. What does it mean? The following. So if you write the octonion as the sum of actually.
But it's not the trace of A plus the trace of B, something, or trace something like that?
No, it's going to be the following. So if you have x0 plus x1i, and then you start again L x2, x4 plus Li, x5, and so on and so forth. Then you ask x0 to be 0. No, this is not, and this is why it gets maybe a bit messy, but it doesn't matter. So like you don't have the x0. So, but nevertheless, what we can do is the following. So define the group G2 as the elements in GL of O tensor R. So here R is an Q algebra, such that if we make G act on X and G act on Y, and we take this non-associative product, this is equal to G acting on X times Y. And of course, this is for all X and Y in the octonions. So we are taking with G2 just the matrices in GL of all that respect this product. And it turns out that G2 you acts transitively on this V7.
What is this product inside of the octonion?
Do you want me to give you the definition?
No, not just in words, maybe. Is this an inner product or something?
It's just like you really want to put a product on this that is non-commutative and it's not associative. So and somehow like I could define it. It's
okay, but it's not an inner product.
No.
You're acting by okay, see.
And of course this is like action. Like maybe I should remove the point so maybe it's less confusing. There is only one product here, which is this.
What is the dimension of Q2 of R?
Wait 1 second. So somehow if I take its Lie algebra,
Yeah, so I look at the tangent space or something like this, but I don't know how many conditions it imposes the quality that you wrote down. That's somehow my question. Does it lower the dimension quite a lot or not really?
I think so, yes, because of quite a lot. So it's Lie algebra is going to be given by something of dimension. So there's going to be the Lie algebra of SL3 plus 2 copies of the standard representation of this SL3. So this is going to have dimension 9 and 3 and 3. So like that's more or less the dimension 14. So like imagine that the group G2 will have dimension 14.
Okay, thank you.
No, this is good. Like this is a good question, and indeed, the point is that the rank of G2 is just like the rank in the sense the rank of the maximal split torus over G2 is just 2. It's not that big, and that's why I think it's called G2. Okay, so there are two funny things about this group G2. I mean, there are many funny things about it, but two that deserve attention, and they are the following. So the first point is that G2 has discrete series. Of course, here I'm taking the real points of G2 as discrete series. But no Shimura variety. Meaning that the locally symmetric space associated to G2 is only a real manifold. And the second thing is that we can realize, instead of looking at G2 like this, G2 can be realized as follows. So G2 can be realized as the stabilizer of a vector of the representation spin, is the spin representation of spin 7. This is actually a orthogonal representation, so this belongs to each other. And somehow the picture that one gives is the following. So G2 of C, of course. G2 of C sits inside SO7 because of its action on the octonions B7. And that's transitively in V7, but it belongs to spin 7. Sorry, and this depends on a choice of a vector. And SO7, well, it what do I want to say? Do I want to write it like this? Yeah, of course, I didn't want to write it like this. Sorry for this. For my notes, it's just better to swap the roles of the arrows. So I'll just put spin 7 here, SO7 here, because there is a spin representation which is SO8 C, and this belongs to GL7. And this belongs to GL8. And so the idea is that this is commutative. And actually G2C is really the subgroup of spin 7, the subgroup of spin 7C given by is really defined by this diagram. So it's the subgroup of GLs of SO8 or GL8 given by the intersection of these two guys. And the last thing that I want to say, so here we have what we call the spin representation. And this arrow that now is not anymore defined by the choice of the vector, this is choice of vector. This is the standard representation of G2 given by these octonions. And what's the fun part of it is that now we're exactly in the case of the example above. So if we look at the spin representation and restrict it to G2C, this is going to split us the standard of G2 plus one trivial line. So the moral of the story is that now if we take automorphic representation associated to the Langlands dual of spin 7, then they should have their spinel function should have a pole at s equal to 1 if they come from G2. And this is, I said it in words, but I'm going to explain it in 1 second. This, I guess, it's section 4. It's really due to it's an insight of Gross and Savin that they say the following. Okay, G2R doesn't have discrete series, but we don't have Shimura varieties, but we would hope to associate to a nice enough cuspidal automorphic representation of G2 a Galois representation. So how do we do it? Well, let's use a theta correspondence. So for us, G is going to be PGSp6, which is given by the elements G in GL6, such that the transpose times J times G is equal to mu J for some mu inside J1. Here, J is a symplectic form, and we can take it to be the 3x3 anti-diagonal blocks where we put the identities and minus the identity. And actually, then we can consider PG, which is PGSp6, i.e. G divided by its center. And associated to G, there is now a Shimura variety, which I'll denote by Shimura of G of level K. This is a Siegel sixfold.
Sorry, Antonio.
Yes.
This decomposition like a standard plus 1, this 1 came from the vector that you choose?
Exactly.
Okay. There is only kind of one that is
you can like if you want, once you have an embedding, so you have to choose an embedding of G2 inside spin 7, and then this is really a branching law, this decomposition by the theory of highest weight. So you can do it with Sage in 1 second.
And the standard is irreducible for G2?
Yes, is the standard is the so it's this is like V7. And it's irreducible. And so like that's why G2 appears in the picture, and you'll see in 1 second what's fun about this, why it appears in what's working with Joaquin and Francesco. So we have a Siegel sixfold, and I'm going to suppose that K will be of this shape today. So for every P that is in sigma, auxiliary finite set of primes, this is just going to be the Eva Ori at P. And I'm going to assume that all over the other finite places, this is just G of ZP inside GZ hat. So we will only work with this because it makes things a bit simpler. So the point is.
Let me ask you a question before you erase this. Okay.
Oh,
so
yeah.
so can you describe the image in SO7 in a similar way? Right. I mean, you when you restrict your representation of the spin to Chi2, you say it's a standard plus one, so the pole explain where it comes from. But can you have a way to say which image in which forms in SO7 comes from Chi2?
That's
I'm just thinking the way of computing. I mean, computing forms on SO7 should be easy because they should be corresponding to forms in quadratic forms in 7 variables. And then my question is whether you can pin down which ones comes from Chi2 in this presentation or not.
Okay, that's a good question, and I need to 1 second to think about. So like you take SO7, you take the dual group of SO7, and so SO7 is going to have a spin representation. Okay, I'll need to think about it. I think that in principle it's possible, but one is on the, okay. So like if you want later, like at the end of my talk, we can discuss it. Try to do this exercise together. Like you take you want to take the dual group of SO7. That on my nose, like I don't want to say stupid things right now, and a certain representation of SO7 such that the composition of that kind happens. So it's not going to be the standard representation of SO7 because it will stay like this. So it must be like a spin representation. And so I guess that for SO7, the spin representation is still 8-dimensional. Okay, I see. Probably. Like the answer is probably, but I never sat down and did it, so I don't want to say something stupid. But okay, at the end of my talk, we can play with these 5 minutes. And I wouldn't be surprised that Ginsburg or some of his collaborators or some of his students have done this. I wouldn't be surprised. Okay, so we have the variety. Now, what's the point? Is that there exists a theta lift from cuspidal forms, actually, like I'll put it like this, from cuspidal forms on G2 to hopefully cuspidal forms of PG. This is not exactly what Gross and Savin use. They only work with the compact form of G2 where cuspidal doesn't make sense, and then they study a certain theta lifting. But Ginsburg and a few collaborators constructed the one for the split G2, and so there is this theta lift, and this realizes weak functoriality, which means that at almost all places, certainly functoriality, certainly at spherical places, for the embedding of G2. So notice the G2C, I haven't said it, but its Langlands dual is still G2C inside of LPGSp6. And the dual of LPGSp6 is spin 7. And now the insight is the following, that if the theta lift of sigma is non-zero, is cuspidal, and one takes pi, an irreducible component of this theta lift, Then such that it's cohomological. And actually, like, we wonder is a discrete series of infinity. Then one can consider the H6 et al. Probably parabolic cohomology of the Siegel sixfold GK base change to Q bar, where now this sigma is going to be related to the bed places of, it's going to contain all the bed places of pi. Take certain like p-ádica coefficients associated to the weight of the discrete series at infinity. And one can consider the pi f isotypic component. So according to the conjectures, somehow to the global conjectures in the Langlands program, and this is that have been studied in this case by Cret and Shin, this realizes the spin Galois representation of pi. So this is 8-dimensional and realizes the spin Galois representation in the following sense. I'll call this VP pi f or VP pi.
Pi rho is something that we call pi line before.
Sorry?
Pi rho that you wrote there.
Pi f.
Pi f.
Is the pi f isotypic component of the cohomology.
Pi f of finite, you mean?
Finite, yes.
Oh, okay.
That's a good point. I never said what pi f was. And in the following, so it realizes the representation in the following sense. Here, associated to pi f, there is a p-ádica representation from the group of GQ, at least conjecturally in general, but once you put some hypothesis, that's the case, with values in spin 7 QP bar. And of course, here everything will depend on embeddings of, like on isomorphisms between QP bar and C, like I'm putting everything under the rag. But the point is that here we can take the spin and land in GL8 QP bar. And this rho pi f p is composed by spin is really equal to VP pi. But one needs to be careful. This is now a statement once pi f as a Steinberg component. This will eliminate all the bad endoscopic cases. So you're really like going to work with something that is stable at infinity and everything is nice. It's a result of Cret and Shin that I'll say it in 1 second. And so the conjecture of Gross and Sabin is, okay, well, we don't know, we don't have a Shimura variety for G2, but this representation, looking at the diagram that I erased, should decompose like this. VP pi should be equal to VP sigma plus 1 plus 1 meaning just QP bar, where VP sigma is somehow the 7-dimensional standard representation, Galois representation of a G2 cast form. But they didn't only conjecture this. So somehow they were interested in constructing this 7-dimensional motif. And so the hope was to construct it through the cohomology of the Siegel sixfold. But the second is that they conjecture that one is the Hodge class of a certain Hilbert modular threefold. This conjecture is maybe from 98 maybe, around that, and it's quite, if you think about it, for this time, it's quite beautiful. They didn't even know that this thing was 8-dimensional, and conjecturing that this one was coming from the image of a Hilbert modular threefold was motivated by some study of local periods for representation in the image of the theta lift, locally at every prime p are ramified.
Can I ask you a question?
Of course, I mean,
how you construct the rho pi f p?
This is a good question.
No, but but from looking at the Shimura variety of what?
So like,
I mean,
your question is how you construct the rho pi f. P is from GQ, actually is a representation of spin 7, right?
So you're
Because
relating that value representation with b pi pi.
Exactly. So this is a theorem that I was going to state right now, due to Cret and Shin. But they have to deeply use the Artus conjecture and the fact that you have some information. So the point is that you want to construct a representation rho pi fp such that once you apply the spin, it becomes the Galois representation associated to the Tate cohomology of the Siegel sixfold, right? But you first want to somehow ideally construct something like this without going directly in the cohomology. So ideally, if you think about it, the cohomology of this realizes only one instance of this Galois representation. You could take another like representation, let's say the standard representation. This time is 7-dimensional, and you would hope to realize it, but you cannot realize it geometrically.
This work of Arnold
and
Cret,
and so good, yeah.
and yes, this is it's for just
P2N.
Yeah, just P2N Galois representation. So it's more this kind of they start that the first the VP pi, no? But they also construct that.
I think that they construct.
They construct both in some way.
Yeah.
Okay.
But I would cheat if I tell you that I know exactly.
No, it's just to know how to think where it come from, more or less.
Yeah, it's this is indeed what I wanted to state is Cret and Shin have a section in their article where they look at the theta lifts from the compact G2, and they somehow prove the first part of the conjecture. And to do so, they use the existence of this Galois representation that they
now I'm confused. You have three Galois representation playing a role here: VP pi,
yeah,
rho pi fp,
yes,
and VP rho, VP sigma.
Yes.
So the first one is constructed in the Tate cohomology of the PGSp6, and this V pi sigma. Where you construct it?
It's not constructing the this. Okay, if someone from the audience knows, would be.
Oh, okay.
Could I on the top of my mind? I don't know.
Oh, okay, just
we can look at it.
It's fine.
Yeah, how do they do it? Okay, that's something.
Oh, it's just a curiosity. It's not. Yeah.
No, it's like.
In some way, you are relating a talk homology of very different Shimura varieties. No?
Mhm. So so from the method of creating Shin, one can say the following. Suppose that sigma is a cuspidal automorphic representation of G2, of course AQ. And suppose that if sigma is equal to the restricted tensor product of sigma B's, then one has the following. So sigma infinity is a discrete series. Sigma P is Steinberg at a finite place. And the theta sigma is non-zero and cuspidal. Then they prove that there exists rho sigma L such that, so rho sigma L is going to be a representation of the absolute Galois group of GQ, or if you want rho sigma FL, G2 QP bar, such that once you use the standard, like once you use the embedding, sorry, I'll call it, I don't know how I call it before, psi inside spin 7 QP bar. Then this diagram commutes once we put here rho pi f, and this is p, rho pi f p. So somehow what they say is there exists a Galois representation of G2 QP bar such that once you use the embedding of G2 inside spin 7 given by the choice of the vector, this is equal to the Galois representation of rho pi fp. The moral of the story is that they just define rho sigma f to be rho pi fp, and they check that the image of rho pi fp sits inside G2. Because pi f is a theta lift from sigma, and so all of its Satake parameters come from the image of a G2. So this is somehow the story, but somehow as a consequence, conjecture, the first point of the conjecture is true. Because they can define VP sigma, and VP sigma is now really it's the standard composed the rho sigma f p. And by the diagram that I had before, this appears in the cohomology of the Siegel sixfold as a component of VP pi.
Why do you expect such a representation? I mean, it's not the L group of G2 that you want to put here there. I mean, right? I mean, if you have an automorphic form of G2, you expect a representation to the dual group, not to the same.
Yeah, exactly. But this is the, if you look at as a G2 as a G2. If you look G2 as a scheme over QP, then it's Langlands dual is G2.
Ah, okay.
Yeah, no. That's
Okay. I was really surprised. Okay.
Yeah, it's a very good point. It's just in this case, it's really the same. And so like once we have this Galois representation, great. Like one can now somehow deduce the first part of the conjecture, and the question is, what about the second part? So like, which is the cycle that appeared that will explain the Hilbert modular threefold? And now I don't know what time is it. Perfect. I have like 10-15 minutes, no? So now notice that this is related to the Tate conjecture associated to this motif. And so somehow, like, we were motivated by understanding if we could construct this Hilbert modular threefold, at least in some cases, and so somehow give us as much as possible a proof of this conjecture of Gross and Savin. And before I state my my result, I mean with Francesco and Joaquin, I want to say something about L functions again. And to do so, I'm gonna write this. So you see the moral of the story of this relation for the people that maybe like some technicalities is that this functorial lifts from G2 to PGSp6 has an important property that is non-endoscopic, meaning that there is a relation between the representation of G2 and the representation of PGSp6 that is as nice as you can hope. And this is why studying the cohomology of the Siegel sixfold for these theta lifts is quite doable. And so like somehow a theorem that follows from the work of many people, and maybe one can look at Savin, but there are like some results of Ginsburg, maybe Rallis, and Sodri, and so on and so forth. Says the following: suppose that pi is tempered, or actually no, sorry for this. I'll actually put myself in the condition of the theorem. So suppose that pi, which is pi infinity tensor p, is such that pi infinity is in the discrete series. Pi p is timebread at p, and
By P is always the theta lift, no?
in this theorem right now, no.
Oh.
So suppose that pi is a cuspidal automorphic representation of PGSp6. Such that those two conditions are true.
Okay, any, not related with any sigma.
Exactly. Yeah, that's a good point. Then pi is tempered, and the following are equivalent. So one is that the Satake parameters of pi p belongs to G2 for every p, not in sigma. And two is that where sigma, again, for sigma, I always would denote a finite set of primes containing the bed primes of pi. And there exists sigma, which is a cuspidal automorphic representation, somebody said exactly, of either G2, where cuspidal makes sense, or its compact form, at infinity, such that pi is a weak functorial lift of sigma via the embedding side again that embeds G2C to spin 7C. But in particular, if any of those holds, the following is true. And any of this means everything, then L sigma of S pi spin has a simple pole at S equal to 1. And the residue at S equal to 1 of L sigma of S pi spin is given by the following. There is the residue of a Riemann zeta function, so P that belongs to sigma of 1 minus P to the minus S, times, and I'll put it here, the value at S equal to 1 of sigma of the standard representation. And the point is that this guy is non-zero. And this again comes from the fact that sigma will be will actually like technically will transfer to a cuspidal automorphic representation with GL7, and so one can then check that this value is non-zero. And this theorem also uses various works of Pollack and Shine. Like it's really like due to many people, but for what is stated, like the remark is, for now, no automorphic period appear. No, because it's this is the, so you want to relate the restriction S equal to 1 of zeta sigma of S to the one to the residue at S equal to 1 of the Riemann zeta function of S, no, which is equal to 1. So the difference between the two is given by the products over sigma, no? So you know that the residue of sigma is equal to 1. Now you write sigma, I mean z of sigma S as the product, as you were saying, of P in sigma, so 1 minus P to the minus S to the minus 1 times zeta of S. And then you take the residue. Okay, you're right. It's P minus 1 to the minus 1. Correct? Yeah. That's a very good point. So, so no automorphic period appears yet. And this is what like I'm gonna mention in the last section of my talk. And so the upshot is that we need to use a specific integral representation of the spinel function. What time is it? Okay. So we'll take E over Q be a totally real et al. Q algebra. And associated to E, there is a certain group that I'll denote by H. It's going to be the group given by G in the restriction of scalars from E to Q of GL to E, which such that the determinant of G belongs to GL1. In particular, notice that, for instance, if E is equal to Q to the cube, then H is going to be a fiber product of three GL2s with the determinant, with equal determinant in each component. Associated to H, there is a Shimura variety, which is Shimura of H, which is a Hilbert, which is the Hilbert modular threefold. And it's a scheme over Q. So its reflex field is Q. And the Shimura of H can be embedded inside the Shimura of G. And this is due to the fact that if you take yes.
Why is a Hilbert threefold if, for example, you take E, as you said, E equals Q times Q times Q will be a product of modular codes,
exactly,
no?
Exactly.
So
it's like possibly degenerate Hilbert threefold.
Okay.
So it's, as you said, it could be a product of a surface and a modular curve. It could be a product of three curves. And the point is that it's essential to look at those degenerate cases. It will be clear in 1 second. And this embedding comes from the fact that you can take the embedding of 3 copies of the upper half plane inside the Siegel space of genus 3 by considering like the 3 complex numbers tau I and form the diagonal matrix tau 1, tau 2, and tau 3. So this is of dimension 6. This is of dimension 3. This gives a codimension 3 cycles in the variety or in the Siegel sixfold. And
so you want E to have dimension 3 over Q?
Yes, exactly.
Okay.
And I'm going to explain it. I'm going to explain why in the following. In exactly the following. So now I'll call this map. I'll call it delta. So the point is that using branching maps, branching laws, one can define the following map from the H0 et al. Of the Shimura of H, K intersected H. Sorry, not et al. They're actually motivic. With trivial coefficients, Q or maybe an extension of Q to H6 motivic Shimura of G of K with values in V3, where V is like a Chow motive associated to an algebraic representation of G. And this is not always true. We need to impose some conditions on V. Okay. And these conditions on V corresponds to imposing the same condition on the weight of an automorphic representation of PGSp6, which comes from G2. But this is more like a technical thing. And so one can define the following. One can consider Zen mod of E to be given by the push forward of delta of the trivial class in the motivic, the characteristic class in the H0 motivic. So of level k-intercepted direction. So this is an element in the H6 motivic. And why are we interested in this? Because we can consider the étal class map of this guy. And this will define an H6 étal thing in Shimura G K VP3. And we take the G, we're now, we base change the variety to Q bar, and we take the Galois invariance. Oh, this guy. Why do we do so? Because by Tate conjecture, this group should be related to, should be non-zero, and should be expressed by generated by some Tate classes. In the case where the Galois representation, and we look at as a pole at s equal to 1. So we are interested in relating this in looking at the image of this guy once we take a certain pi f isotypic component associated to a theta lift from G2. And here is
Antonio,
yes.
So behind all this construction,
Yes,
you have V. This is the
Yes.
algebraic representation.
Yeah.
That is given by the weight of some automorphic representation, I can imagine.
exactly.
So behind everything, there is an automorphic representation fixed. An automorphic representation
There
of,
is
of the last.
by Ariel. Sorry that it took too much time. But thank you for the questions.
It was a really nice talk. I'll hear the rest of it later.
Okay.
Thank you.
Ciao.
Ciao.
Yeah.
And this is what I'm gonna fix now, exactly.
Oh, okay.
Because it makes sense, and if you want in another, like over a coffee or something, I can tell you which are the weights. And this was like motivational to see that we were in the right track, because the representations V such that this map exists are exactly the one for which the weight must come from G2. The weight of the associated automorphic representation must come from G2. So this was like for us a sanity check that we were in the right.
So is the automorphic representation is in the theorem of the last section or something like that of PGSp6.
Exactly. Okay. Exactly. And this is the point that I'm gonna say now. So the theorem is the following. Suppose that sigma, which is given by this restricted tensor product of sigma v's, is a cuspidal automorphic representation of G2 AQ such that the following is true. So sigma infinity is a quaternionic discrete series. So for people that do not know what quaternionic discrete series, remember G2 doesn't have a Shimura variety. So there's no really holomorphic stuff. But quaternionity is as nice as you can get to the holomorphic stuff. Such that sigma p is equal to Steinberg for all bed primes p sigma. This condition is just to make sure that the multiplicity, that in cohomology, we see an 8-dimensional representation and not something bigger than that. So it's just a technicality for now. Then we can consider pi inside theta of sigma. So if a certain not S, sorry, if a certain integral over the places, the ramified places, and infinity, which depends on pi, is not zero at S equal to 1, then the following is true. The projection to the pi f isotypic component associated to the et al. Realization of this motivic class I'm gonna say it in 1 second. If a certain ramified integral is non-zero, so you take the Tal cycle class map of this cycle, you project it to the pi f isotypic component, and this generates the trivial line in VP pi. In particular, Gross, Savin, conjecture holds. I now I enunciate a theorem that proves this theorem with some other applications, and then I'm done. And I still have to tell you what I sigma infinity is, but wait 1 second.
I think in 10 minutes, you think it's fine? 10?
Even 5.
Oh, it's perfect, yeah.
Yeah, I thought I was taking less time, but
It's our fault because we ask always a lot.
no, it's good. It's good. It's like I wanted to, since on Monday I gave a general talk. Today I wanted to get hands dirty, and I hope you get something out of this. But the point is that, so the theorem says the following. So I'm gonna adopt the same notation as in theorem 2, okay? As in theorem 1. As in theorem 1. Sigma and pi are as in theorem 1. So suppose that, again, this I sigma product in I sigma union infinity of pi s. So pi 1 is non-zero. Then, if one looks at the Betti realization of the motivic class, this is really the cycle class Betti map of motivic of E, and pairs it with a good enough form psi, compares it with the differential form of associated to a cast form of pi using Poincare duality, then this is equal up to a non-trivial value, which is exactly given by this integral, to the residue at s equal to 1 of L sigma s pi spin, which, by what we noticed soon ago, this is related to L of 1 sigma standard, which is non-zero by our hypothesis. And what is the conclusion in particular? This equality gives us the following. So point 1 is that minus the order at s equal 1 of the spinel function is less or equal than the dimension as a complex vector space of the motivic homology of the Shimura variety for G with level K and V3 is less or equal than the dimension of the motivic homology modeled out by the kernel of the cycle plus Betti map. And two, what do I want to say? The last thing is that the map from this motivic group, so of Shimura, of G, of K, of V3, home. So there is a map that is the twisted cycle Betti map that actually lands in the H7 Hodge of the variety. Is the complex variety, but now we're looking at the invariance by by complex multiplication, and the invariance in the coefficients. This is surjective. So these are the two theorems, I mean, main theorems that we proved. And here in this like 2 minutes, I'm gonna just say a couple of words. So why I wanted to stress out these two points. So yes. Yes, I'm losing it. So Tate conjecture suggests like an equality between those two numbers. And what we can prove is, okay, we don't know exactly, I mean, Tate conjectures suggest an equality here. We cannot actually prove that these are equal because we don't have control on this motivic homology group. However, we can construct an element here, which is non-zero if this is at least 1. And so if we had more control on the motivic homology group, like example, knowing how to construct the motif themselves, then one could try to prove something like this. And also that there is this Beilinson conjecture that is on relating the H7 to a certain motivic part. Again, the contribution from cycles should come when this pi f when the L function of pi f as a pole, we cannot somehow see this as an isomorphism again because we don't have control on the motivic, but this gives a good result towards Beilinson-Delin conjecture for this. And the last remark that I want to make, which is very important, is about I sigma. The fact is that this I sigma union infinity pi 1 is non-zero implies that E is equal to F plus Q. So it implies that E has to split as a totally real field extension F plus Q. And where does this I sigma infinity appears? For the following reasons. Because in order to prove this, we show that this thing, which is equal to the integral over H modeled out by the adelic points of the G of a certain psi tilde H dH. Psi tilde is because there are certain differential operator that appears at infinity. This is related to the residue at s equal to 1 of an integral, where now h is, and this is essential. So like this is somehow a technical delicate point. Somehow you need to make sure that your branching laws are compatible with the Archimedean theory. And this is a result of Pollack and Shah, and crucially uses that E is equal to F plus Q, where one sees this integral as the integral of an isoscene series on GL2. And this is why we needed to split. This is on GL2. Paired with psi tilde H. And the point is that Pollack and Shah show that this is equal to the partial function S pi spin times an integral at sigma and infinity pi of S. And this is just nothing but the integral, or is this integral only over sigma and the infinity place. And the point is that you want that this is non-zero at s equal to 1 to pull out the residue of the function. And sorry, I run like really over time a lot, but that's it.
Do you have any question, more comments to Antonio?
I guess I killed everyone.
We still have 7 minutes till we lose the room. So. Paquin.
Maybe Paquin?
Yeah, I guess I'll ask a question also on behalf of Daniel. So have you guys thought about interpolating these residues in p-adic families?
So this is certainly something that that is interesting, no? But there are two possible directions that you could use. One is to interpolate these periods.
Yes.
So you take our class and you p-adically interpolate it, and I think it's really doable. And it's very similar to your situation, just maybe with higher groups.
Mm-hmm.
But there is a different approach that would be you can p-adic vary this integral.
Yes. So put the Eisenstein series in a family. Exactly,
and this is related to the construction that I have with Joaquin on Eisenstein classes. I mean on this vertical or on this like norm compatible classes in the cyclotomic variable that we published in Documenta, and this would give you certainly like a stronger variation, but with the problem that this period is directly related to the L value that you would like to pick, while this integral would naturally see a 8-dimensional, like a 8-dimensional or a degree 8 Euler factor, and not the degree 7 that you want. So it would be similar to what Sara and David do for the symmetric square, I think. But yeah, like that's a very good point. One could try to do that. Issues is to calculate the Euler factor P.
Mm-hmm.
That could be one of the main difficulties. But yes, certainly this could be done, and we'll give like a there would be like 2 weights of the weight space of GSP6 that will be p-adically interpolated.
More questions? Comments, maybe? So if not, let's thanks again, Antonio, and thanks a lot for